Hello everyone, I'm Dev Shakya, and today we're diving into something pretty amazing. A constant, invisible storm of particles from deep space that's bombarding our planet, and you right this second. We're talking about cosmic rays, the universe's most extreme and honestly most mysterious messengers.
No, really, just think about that for a moment. As you're sitting here, particles that have traveled for millions of years, moving at nearly the speed of light, are passing right through your body. So the big questions are, what are they? And where in the universe do they come from? All right, so let's rewind the clock a bit. The story starts over 100 years ago. Scientists had these instruments called electroscopes, and they kept noticing that they'd mysteriously lose their charge. Something was ionizing the air. So in 1912, a physicist named Victor Hess did something incredibly bold. He got in a hot air balloon and went way up. And what he found was wild. The higher he went, the more intense the radiation got. The conclusion was inescapable. This stuff wasn't coming from Earth. It was coming from outer space.
Now, here's the first big twist in the story. The name they came up with, cosmic rays, is actually wrong. It's a total misnomer. These aren't rays like light or X-rays. Nope. They are actual physical particles, the cores of atoms, totally stripped of their electrons, zipping across the universe at unbelievable speeds.
So if they're particles, what kind of particles are we talking about? And what kind of cosmic fireworks display could possibly be powerful enough to shoot them across galaxies? Let's get into it. So this chart breaks it down for us really nicely. The vast majority, we're talking almost 93%, are just good old-fashioned protons, the nucleus of a hydrogen atom. Then you've got about 6% that are alpha particles, which are just helium nuclei. And then there's this tiny little sliver of everything else, the cores of heavier elements.
But what's really mind-blowing is the energy these things carry. Just look at this spectrum. The most powerful cosmic rays have energies millions, even billions of times greater than what we can cook up in our biggest particle accelerator on Earth, the Large Hadron Collider. It's not even close.
So, where does that kind of insane energy come from? Well, you need the most violent events in the cosmos. Think exploding stars, supernovae. The shockwaves from these explosions create these huge, tangled magnetic fields that act like a kind of cosmic pinball machine. Particles get trapped, bouncing back and forth, and with every single bounce they gain more and more energy. That process, that's what we call Fermi acceleration.
Okay, so a particle gets shot out of a supernova, travels for eons, and finally, it gets to our little blue planet. But before it gets here, it has to face our planetary defense system, Earth's magnetic field. And this magnetic field gave us one of the first huge clues about what cosmic rays really are. See, scientists noticed something funny. The number of cosmic rays you detect depends on where you are. There are fewer of them at the equator, and way more as you get closer to the north and south poles. This became known as the latitude effect.
So what does that mean? Well, if the Earth's magnetic field can bend their path, they can't be neutral particles. They have to have an electric charge, which of course led to the next obvious question. Okay, are they positive or are they negative?
And this is where the detective work gets really clever. Physicists figured that, based on the way our magnetic field is oriented, if the particles were positive, they get deflected in a way that makes more of them show up from the west. And when they checked, that's exactly what they found. More particles coming from the west than the east. A clear east-west asymmetry.
And just like that, the case was closed. All this evidence from these geomagnetic effects pointed to one undeniable conclusion. The primary cosmic rays arriving from deep space are overwhelmingly positive.
So we've got our positive particle, probably a proton, that has survived its journey across the galaxy and navigated our magnetic field. But its journey isn't over. Its grand finale, its big finish, happens when it slams into our atmosphere.
Now, a primary cosmic ray doesn't just quietly pass through. Oh no. As you can see here, it smashes into the nucleus of an air molecule in an incredibly violent collision. And this one impact unleashes a chain reaction, a spectacular shower of secondary particles that can spread out to cover an area the size of a city by the time it reaches the ground.
This initial cataclysmic collision has a name you'll want to remember: spallation. The primary particle literally shatters the target nucleus, creating a spray of brand new, lighter particles. And some of the most important ones created are these really short-lived particles called pions.
From that first collision, the shower that's created basically splits into two different stories happening at once. You've got what's called the soft component. That's a cascade of electrons, their antimatter twins called positrons, and photons. And then you have the hard component, made of these super tough, highly penetrating particles called muons.
So let's follow that soft component for a second. It kicks off when a neutral pion decays almost instantly into two high-energy photons. Then, one of those photons can pass by a nucleus and, poof, transform its energy into a pair of particles, an electron and a positron. That's called pair production. Then those particles create more photons, which create more pairs, which create more photons. You get the idea. It's a runaway avalanche of particle creation.
You know, we can actually see this happen in the lab. This graph is called the Rossi transition curve. It shows that as you pass these particles through a block of lead, the shower builds up, the number of particles hits a maximum, and then it starts to get absorbed and dies out. It's the exact same principle that's happening high above us in the atmosphere.
But what about that other storyline, the hard component? Well, this quote says it all. The charged pions created in that first collision decay into muons, and muons are the tough guys of the particle world. They just don't interact very much, so they can slice right through the whole atmosphere and even burrow deep into the ground.
But wait, there's a problem. Muons are really unstable. They only live for about 2.2 microseconds. That's not nearly enough time for them to travel from the top of the atmosphere down to us. So how do they do it? The answer is Einstein. It's special relativity. Because they're traveling so close to the speed of light, time itself slows down for them. From our perspective, their internal clock is ticking in slow motion. This is called time dilation, and it stretches their tiny lifespan just enough for them to complete the journey. It's amazing.
So all of this constant shower of exotic particles, it basically turned our atmosphere into a giant, free-to-use particle physics lab. This was humanity's first particle accelerator long before we ever dreamed of building our own.
And the discoveries were groundbreaking. I mean, look at this picture. It's one of the most important photos in the history of physics. In 1932, Carl Anderson saw this track. He saw a particle curve one way in his magnetic field, go through a lead plate, lose some energy, and then come out curving more sharply, but in the exact same direction. An electron would have curved the other way. This was something with the mass of an electron, but with a positive charge. He had discovered antimatter. This was the positron.
And that was just the start. The muon, the particle we were just talking about, was found in cosmic rays in 1937. And the pion, the particle that starts the whole atmospheric cascade, was finally pinned down in 1947. For decades, cosmic rays were our only real window into the bizarre world of subatomic particles.
So you see, the universe is constantly sending us these little postcards, encoded in high-energy particles. They've taught us about antimatter, about relativity, about the very building blocks of our reality. And even today, they still hold clues to the most violent and energetic places in the cosmos. You just have to wonder, what secrets are they going to reveal to us next? Thank you.